Hello everyone and welcome back. My name is Mr. Kovault, and in this video I'm going to be going over some stoichiometry involving a redox reaction. So let's get into this. So you have a solution of sodium oxalate Na2C2O4 is titrated with KMnO4, potassium permanganate, and the redox reaction shown below occurs if 0.2482 grams of the sodium oxalate is dissolved in water and titrated with 23.68 milliliters of the potassium permanganate. What is the molarity of the potassium permanganate? Okay, and then they give us this unbalanced redox reaction. One of the things to keep in mind is that it is in acidic solution. So the first thing we need to do in order to use this equation for stoichiometry is we need to balance, because right now we have an unbalanced equation, and so we need to balance it so we can get the coefficients that we need for the mole ratios. Okay, so how do you balance a redox reaction? Balancing a redox reaction is similar, but not the same thing as balancing a normal reaction. There's more steps involved. So I'm going to go over the balancing of the redox reaction, and then we'll go into how to use that to do stoichiometry to get the answer to our question. Okay, so the first thing you need to do when you're going to balance a redox reaction is you need to identify what the formal charges are, or what the oxidation states is. So what are the oxidation states of each element? So the way you find the oxidation state is one of the rules is the oxidation states of all the atoms in your compound must add up to the overall charge if there is any. So in this case, the oxidation state of oxygen is 2 minus, or minus 2. And one thing I want to point out is notice that I'm putting the negative first. That indicates that this is a oxidation state or oxidation number. If you put the negative after the number, if you put the sign after the number, that is indicating a charge. So that is a technicality that you should be aware of. So this is oxidation state -2 for each of the oxygens. We have 4 oxygens, so that means that the total negative is -8, right? So that's going to be -8. So the oxidation state of the manganese has to add up with the -8 in order to give a total of a -1. So that means that the oxidation state of manganese here has to be a +7. So 2 times 4 gives us -8. -8 plus the 7 gives us a -1. So those are the oxidation states of manganese and oxygen here. Here, same thing. Start with the oxygen. Oxygen takes precedence. So again, we'll give oxygen a -2 for its oxidation state. Again, we have 4 oxygens, so that's going to be -2 times 4 gives us a -8 again. And again, we have a 2 minus charge on our oxalate ion. And so that means that whatever the carbon is, the total has to be equal to such that we get a 2 minus charge on our ion here. So that means that in order to get a 2 minus charge from the -8, the 2 carbons have to have an overall oxidation state of a +6. Because +6 and -8 gives us a 2 minus. And so so that means that the 2 carbons together, their oxidation states must equal a +6. If we divide the +6 between the 2 carbons, that means that each carbon would have an oxidation state of a +3. So that tells us that the oxidation state on the carbon is a +3. Next, we have our products. So whenever you have a monoatomic ion, the oxidation state is the same as the charge on the ion. So here it's a +2 oxidation state. And here, same thing. Here we're going to start with oxygen because oxygen takes precedence over carbon. We're going to give oxygen a -2 oxidation state. We have two oxygens, so that's going to give us a -4 total. And notice that there's no charge on the carbon dioxide. That means that the oxidation states of all the atoms must equal 0. So if we have a -4 total for our oxygens, that means we should have a +4 total for the carbon. We only have one carbon, so that oxidation state goes on to one carbon. So that's going to be a +4. Let me write that up here. So that's going to be a +4 for the carbon. And so let me go ahead and erase these. Okay, so now that we're done with that, the next step is to divide up the half reactions, or divide up the redox reaction into two half reactions. One half reaction is going to be the reduction half reaction. The other one is going to be the oxidation. So let's remind ourselves, oil rig stands for oxidation is loss of electrons, reduction is gain of electrons, or if you are familiar with Leo-Gur, so Leo, loss of electrons is oxidation, Gur, gain of electrons is reduction. So those are good mnemonic devices to remember what is what. So oxidation is the loss of electrons. When you lose electrons, you become more positive. So what element becomes more positive? If you look at the carbon, here it was a +3. Here it's a +4. So it became more positive, so it lost electrons. So the carbon is undergoing oxidation. So we're going to write that as the oxidation side of the reaction. And then if you look at manganese, manganese goes from a +7 to a +2. So here, +7 to +2, that indicates that there was a gain of electrons, right? So when you gain negative electrons, you become less positive. So here, you've got a +7. Here, you've got a +2. So there was a gain of 5 electrons. We'll talk about that in a moment. So we know that the gain of electrons is reduction. So the reduction half reaction is going to involve manganese, KMnO4, and Mn. So we're going to now separate those out. So we're going to have reduction. So the reduction half reaction is going to be MnO4, 2-, and that's going to go to Mn2 on this side. And then the oxidation, I'm going to go ahead and remove this. So then on the oxidation side, so for oxidation, we saw that the carbon undergone oxidation. So here we have C2O4-, the oxalate ion. So we're going to have that here. So C2O4, 2-, and that's going to go to carbon dioxide on this side, CO2. Okay. Let's go CO2. Yeah, CO2. Let me double check. Okay, so now we have the separated half reactions. This is the oxidation half reaction. This is the reduction half reaction. So now we're going to balance both of the half reactions, and we're going to go through step by step. So the first thing you want to do is balance the atoms. Just balance it like you normally would for a redox react or for a normal reaction. There'll be one thing that'll be different, but I'll talk about that in a moment. So first we want to balance the atoms. So here we have, let's do the oxidation since that's going to be clear. So here I have 2 carbons. I want 2 carbons on this side. So I'm going to put a coefficient 2. And then I have 4 oxygens. And then here I have 2 times 2 is 4 oxygens. So I balanced atoms on both sides. So I'm done with this part, but I have more to do. Notice that there's a charge here. We'll have to balance charge later. But right now, the first thing you want to do is make sure that the number of atoms on both sides are the same. Okay. Now, what about this side? So again, I'm going to balance the atoms. So I have 1 manganese here. I have 1 manganese here. Ignore the charge. So we're just counting atoms. So 1 manganese, 1 manganese. Okay, that's good. Now, I have 4 oxygen over here. I have no oxygen over here. So what do? So this is where the acid solution comes in, right? So also the fact that this is in water. So if I have 4 oxygens over here, I'm going to balance the oxygens on this side by adding water to this side. So I'm going to add 4 water molecules. Why? Because this is in solution and it's in water. So I have 4 water molecules over here. So now I have 4 times 1 oxygen. I have 4 oxygens on this side. Okay, but now I have another problem. I have 4 times 2 is 8 hydrogens. I have 8 hydrogen on this side, but I don't have any hydrogen on this side. Well, how do I get hydrogens on this side? That's where the acid comes in. Your acid indicates that you have H plus ions in solution. So we're going to add H plus ions to balance the hydrogen. So on this side, we're going to go ahead and add 8 H plus ions like that. So now I have 8 H hydrogen on this side. I have 4 times 2, I have 8 hydrogen on this side. Now I have the right number of atoms. So now I have balanced the number of atoms on each side of the reduction half reaction. So now I'm done with balancing the atoms. Now, the next thing you need to balance is the charge. So we need to make sure that the charge on both sides of the arrows adds up to the same amount of charge. So we're going to do that by adding electrons either on one side or the other in order to balance charge. So here I have 2 negative. I only have 1 of these. So I have 2 negative charges on this side. So that's 2 negative on this side, but it's 0 charge on this side. So I need to make this side have a 2 negative charge. So I'm going to add 2 electrons. So now there's my 2 electrons. Now the negative charge is balanced on both sides. The charge is balanced on the reactants and product side. Now I got to do the same thing over here. So here, let me double check that charge for a moment. Yep. This should be a minus charge, not a minus 2. All right, so here I have a 8 plus charge. I have 8 hydrogen ions. All of them have a plus charge, so that's 8 positive plus I have 1 negative here. So if it's 8 positive plus 1 negative, that's going to give an overall positive 7 on this side. But here I have neutral water, that's 0 charge. And then I have the manganese ion with a 2 plus charge. So I have a 2 plus charge on this side, but I have a 7 plus charge on this side. So I need to get these equal. The only thing I can add are electrons. Electrons are negative. So I'm going to have to add the negative electrons to this side in order to reduce the 7 to a 5, or I mean to a 2. So I need to add 5 negative electrons to make this a positive 2 charge total. So I'm going to go ahead and add the 5 electrons. So there's the 5 electrons. So 5 negatives plus 1 negative is 6 negatives, plus 8 positive gives me a total of 2 positive, which matches the 2 positive on this side. So now both of my half reactions are balanced in the number of atoms and the number of the amount of charge on both sides. Okay, now the next thing I want to do is put these back together again. So I split them into halves. Now I want to make it whole again. But before I do that, I need to make sure that the electrons cancel out. So notice here I have 5 electrons, and here I have 2 electrons. So when I add these together, the electrons are not going to cancel out. Here I have 5 electrons on the reactant side. Here I have 2 electrons on the product side. They're not going to cancel out completely. So I need to multiply my half reactions by a factor that's going to allow or get the electrons to be equal amounts. So here I have 2, here I have 5. So what do I multiply? Well, if I multiply this by 5, I get 10 electrons. If I multiply this equation by 2, I get 10 electrons. So that's what I'm going to do. So I'm going to multiply this by 2, and I'm going to multiply this by 5. So when I multiply this by 2, I get 10 electrons plus 16 hydrogen ions plus 2 KMnO4 minus ions. And then I'm going to get 2 Mn2 plus 8 water molecules. So now I have this with 10 electrons, and then I do the same thing over here. So I'm going to have 5 C2O4 2 minus. Multiply this by 5, that's going to give me 10 carbon dioxide molecules. And then 5 times 2 is 10. 10 electrons. So now I have 10 electrons on this side. I have 10 electrons on the reactant side here, 10 on the product side. When I add these together, the 10 electrons on the product side and the 10 electrons on the reactant side are going to cancel each other out. So what I end up with is 16H plus 2 MnO4 minus, right? And then I got to add the reactants here. So this reactant is going to go on this side. So that's going to be plus 5 C2O4 2 minus. Now I got all the reactants together. Now I'm going to take the products. So I'm going to add these products together with this product. Remember, the electrons here are canceling out, so I'm not going to include those. So I'm going to have 2 Mn2 plus, oops, that should be 8 H2O molecules plus, so now I've got that added together. So now I'm going to add the 10 carbon dioxide molecules. So now I have everything added together. So this is my complete balanced equation for this redox reaction. Now that I have a balanced equation, now I can use the mole ratio here to help me convert and figure out what the molarity of the KMnO4 is. So again, to remind ourselves what molarity is equal to the moles of the solute over liters of the solution. So all we need to do is find moles, find liters, divide, and we've got our molarity. Okay? So let's get into this. So now that I have my balanced equation, now we can go to the information. So they said that if 0.2482 grams of the sodium oxalate is dissolved in water and then is titrated with 23.68 milliliters of KMnO4, what is the molarity of the KMnO4? So we know the molarity, we know the liters or the milliliters of the KMnO4. Here we know the grams. So what we need to do is find the moles of the KMnO4. And they gave us the volume of the KMnO4. So we need to convert the volume to liters. So all we need to do is find the moles, but they gave us grams of the sodium oxalate. So we can use that to convert from grams of the sodium oxalate to moles of the sodium oxalate using the molar mass. And then once we got the moles of the oxalate, we can use the 5 to 2 mole ratio, and then we can get the moles of the MnO4 minus. But keep in mind that the moles of the KMnO4 minus is equal, of the MnO4 minus is equal to the moles of KMnO4, because potassium and the permanganate is a 1-to-1 ratio. So 1 mole of the whole gives us 1 mole of the MnO4. So if I find the moles of the MnO4 minus ion, it's going to be the same as the KMnO4 formula. So let's go ahead and do that. So I'm going to start with 0.2482 grams of the sodium oxalate over 1. And now I'm going to use the molar mass. So I got to use molar mass to convert grams to moles. And the molar mass is 133.9988. So 133.9988 grams of sodium oxalate. Okay? So now that I have that, I'm going to convert that to moles. So I want 1 mole of the sodium oxalate on top. So grams of the sodium oxalate cancel out. And now I have moles of the sodium oxalate. Now I can use my mole to mole ratio here. So 5 moles of this, right? And again, you'll notice that the moles of the oxalate ion is going to be the same as the moles of the whole substance. So whatever the moles of this is, it's going to be the same as the moles of the sodium oxalate. So 5 moles of this is the same as 5 moles of the sodium oxalate, and that's going to be related to 2 moles of the MnO4, which is the same as the 2 moles of KMnO4. So I'm going to write it that way. So since I have on the top moles of the sodium oxalate, I'm going to have 5 moles of the sodium oxalate on the bottom. And then on top, I'm going to have the 2 moles of the potassium permanganate. So 2 moles of KMnO4. So now moles of the sodium oxalate ion substance cancels out. Now I have moles of the KMnO4. Now I'm done. So I have moles. So now all I need to do is multiply across the top, divide by the bottom, and I'll get my answer in moles. And when I do that, I get 0.0007409. 7409. So that's going to be 0.000. Let me double check. 7409. 74090. And so, oops. Sorry about that. And this is going to be moles of the KMnO4. Okay, so now to get the molarity, all I do is I take the milliliters, right? Convert that to liters. So let's go ahead and convert that to liters. So 23.68 milliliters over 1. I know that 1 milliliter is equal to 1/1000th of a liter, because milli is 1/1000th. That's what milli means. So I'm going to put 1 milliliter on the bottom, 10 to the negative 3, or 1/1000th liters on top. Again, you could do 1,000 milliliters is equal to 1 liter. It's the same ratio. So here, milliliters cancels out, and now I get my answer. So I'm going to convert milliliters to liters, and so this is going to be 0.2, oops, 0.02368 liters. So now all I need to do is take the moles, divide it by the liters, and I get my molarity. So 0.0007490 moles of the KMnO4 over the liters of the KMnO4. So this is 0.02368 liters KMnO4 solution. So I just divide that, and when I divide that, I get 0.03129. So 0.03129 molar. And so that, ladies and gentlemen, is the molarity of the KMnO solution. And so as far as sig figs go, remember, your answer should have the same number of sig figs as the least number when you're multiplying and dividing. So you can see in all the calculations, I have 4 here. I have, 7 here. This is exact. So I end up with 4 sig figs, but I have 5. So I carried an extra digit. And then, of course, I have 4 sig figs here. So here, again, the 9 is underlined. So I have 4 here, 4 here. So the least number is 4. And that's what I have. I hope this is helpful. I hope you enjoyed the video. I hope you learned a lot from this video. If this helped you in any way, then please, by all means, like the video. Hit the like button somewhere over here. Also, support the channel. Hit that notification bell. Subscribe to my channel. When you hit that notification bell, make sure that you click all so you can be notified by all the videos I put out. Finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. If you have any question or problem you need help with, or if you have a topic you want me to cover, let me know. I would love to do that for you. Thanks for joining me, and have a great day.